Hi, welcome. Today's lesson is logarithmic differentiation. We'll talk about the concept, we'll work through a problem, and then we'll do another problem. The idea here is that the function may be too messy to do directly, and so we're going to do something ahead of time that kind of tweaks it. So an example here, I want to take the derivative of 1 plus 6x all to the 8th times 3 minus x all to the 7th. You can do this. It's doable directly. It's a product rule where each piece is a chain rule, and it can be done directly. But if you don't want to do it directly, what we do is we tweak it. We take the natural log of it. Now the natural log of something is the natural log of the pieces inside. So it's the natural log of 1 plus 6x to the 8th times 3 minus x to the 7th. Now why did I do that? Because rules of logs allow me to manipulate this. Something times something. Inside a log is this first something plus the second something. Now rules of logs go further. That power of 8 comes straight out. This is not taking the derivative. This is rules of logs. Likewise here, that 7 comes straight out. Okay, that's what the natural log of y is. So when I take the derivative of the natural log of y, I'm just taking the derivative of all of this. That's all I'm doing. So the derivative of that first piece, it's 8 times something, so it's just 8 times the derivative of that something. The something here is the natural log of some function. We have a rule for that. The derivative of the natural log of some function is going to have that function on the bottom and the derivative of it on the top. Likewise, the other one. We have 7 times, on the bottom goes the function inside, and the top goes the derivative of that function, which is minus 1. I'm going to simplify this a little. I get 48 over 1 plus 6x minus 7 over 3 minus x. Now, do I have to combine those into a fraction? Maybe, but not yet. Why not? Because now I'm going to simplify. What is the derivative of the natural log of y? The derivative of the natural log of y, using the rules of logs, is going to be y prime over y. So what would I do if I want to simplify and find y prime? Y prime over y is that. So what I want is y prime. So I multiply both sides by y. So we get y prime is, what do we have there? 48 over 1 plus 6x minus 7 over 3 minus x times y, because I have to multiply by y. Why is that? So, let's simplify this. Multiply this in here. One of the powers of 1 plus 6x cancels. I get 48, 1 plus 6x. There's only 7 powers left. 3 minus x, 7 powers left. And then minus, I'm dividing by 3 minus x, so one of these powers goes away. I have 7. 1 plus 6x to the 8th. 3 minus x to the 6th. But I'm not done, because now I have 2 terms. I want to simplify this more. That was what logarithmic differentiation did. It allowed me to get to here. But to simplify it more, I have to do a little algebra by factoring out. I have a lot of powers of this. So if I factor them out, 1 plus 6x. How many do I have? 7 here, 8 here. So I have at least 7 everywhere. How many 3 minus x's do I have? To the 7th power, to the 6th power. I have at least 6 everywhere. So what do I have left over? 48. And what do I have left over? All of those are used up. One of those is left. Minus. Here, 7 is there. What's that? Well, 7 of them are used, so I have 1 left over. And all of those are used up. Now, if I want to simplify this, what do I have? 48 times 3 is going to be 144 minus 48x minus 7 minus 42x. So all of this turns out to be 1 plus 6x to the 7th, 3 minus x to the 6th, and then 137 minus 6x. If that seemed like a messy, ugly problem, then you got it right. This is messy. It's ugly. There's a lot of mush to it. But if you work it carefully, you can get to the answer. So try one more. Where does this have a horizontal tangent line? Okay, if you're not so sure what that means, horizontal tangent line means the derivative is 0. Okay, so how do you do that? Well, you do it the same way. You can take logarithmic differentiation. Take the natural log of both sides. So we get, doing both the steps that we worked out there, 2 ln x plus 4s plus 6 ln 3x minus 1s. Now if I take the derivative, y prime over y will equal, what's that? The derivative of that will be 2 times 1 over that times its derivative plus 6 times 1 over the derivative of 3x minus 1 times its derivative. Now this time, I'm going to try to combine those before I bring the y over. So I have 2 x plus 4s plus 18 3x minus 1s. So what is that in terms of? I've got an x plus 4 down here. I've got a 3x minus 1. To get a common denominator, I have to multiply by the opposite thing. So this one I'm multiplying by 3x minus 1 over 3x minus 1. So I get 2 3x minus 1s plus 18. To get both of those in the bottom here, I multiply by x plus 4 over x plus 4. On the top, I have 6x minus 2 plus 18x plus 72 all over x plus 4 times 3x minus 1. On the top, I get 24x plus 70. Just to refresh your memory, that's what y prime over y is. I want y prime by itself. So multiply by y, which is that. I'm going to get y prime equals 24x plus 70 over x plus 4, 3x minus 1, times, there's an x plus 4 squared, there's a 3x minus 1 to the 6th. Now, this method of doing it first, getting a common denominator, might be nicer, because I can now, this factor times this factor times this factor, I can cancel factors. I'm dividing everything once by x plus 4. I'm dividing everything once by 3x minus 1. So I get y prime is 24x plus 70 times x plus 4 to the first times 3x minus 1 to the 5th. I'm almost done. I just need to set that to 0. If that's 0, it means one of these three things is 0. This one, it means x would be, bring that over, you get minus 70 over 24. That simplifies, but I don't care right now. If I do this one, I get minus 4. And if I do this one, the fifth power, is something to the fifth power 0? It just means that something is 0. Bring the minus 1 over, it makes it plus 1. You get 1/3. Hopefully, the concept of logarithmic differentiation makes sense. And you just recognize it's going to be messy because if it were an easy derivative, you wouldn't bother. So this was really applied to the yucky ones. But it makes the yucky ones less yucky. Until next time, this is Dr. J.